promise you I'll give this efficiently. I need to be somewhere else at 11:30, so it'll be done on time. Yesterday, Mark Stivers gave a talk that's related. This comes out of Wisdom of the Crowd work that Mark and I have been doing for a number of years now, 5, 6 more years. And we wanted to make sure we didn't talk about the same thing, or at least not in great substance. So we agreed that I would talk about sport and he could talk about anything else, and that's a nice way of delineating. So I'm going to be talking about cognitive approaches to wisdom of the crowds for making sports predictions and using crowdsourced data to fit with the theme of the workshop. Wisdom of crowds often talked about as one monolithic thing, but I think it really comes in 3 different parts, and I think it's interesting to dissociate those parts. So let's do that in a sporting example. Who's the current captain of the Australian Test cricket team? Anybody? We're probably... Sorry?
Andrews.
No. We're probably waiting for an Indian to come back into the room, and then we might get the answer. But if you extend the crowd far enough, if we wait for enough people to walk through the room, somebody will say it's Steve Smith, and that'll be the right answer. So you've just extended the crowd far enough until somebody actually knows the answer, and that would be the simplest sort of wisdom of the crowd. You could ask a question like, how many NBA championships have the Chicago Bulls won? And now everybody could probably have a go at this. There could be a whole lot of estimates, and we might do something like take the mean or the median of those estimates, and the idea would be by doing that there's a common signal, which is the true number that the Chicago Bulls has won, and everybody has idiosyncratic noise associated with that, and so as we go through an averaging process we amplify the signal and cancel the noise, and the crowd becomes wise with everybody participating in this numeric answer. And then there's a third type, which is something like list the last 50 World Series MLB champions. World Series in inverted commas in quote marks here because it's only teams from North America, not teams from the entire world. And you could imagine going through and doing that. One answer might be, who cares, baseball is boring, which is the answer I would subscribe to. But if you really wanted to tackle the question, you could start to piece together bits where you got some old timers who remember the 1970s, or people who could do all the ones that their team had won but not anybody else's team, and other people who remember the recent ones. And you could start to do some sort of jigsaw puzzle completion as you put together this list. So I think all 3 of those, the idea of extending to an expert, amplifying a signal, or completing a jigsaw puzzle, are examples of wisdom of the crowd, but they're kind of a little bit different. What they have in common for a cognitive modeler is that all of the raw data that were generated there, the answers, the numerical estimates, the lists, the partial lists, were fundamentally human behavioural data. The data that are being combined are behavioural data, and so they're the outcomes of cognitive processes, and they're generated by people's knowledge. And the second thing you note is that in all of those approaches you needed some sort of variability in people, some sort of individual differences. So the first of those observations looks to a cognitive modeler like, we need to model this. We need to model the cognitive processes that generated the behavioural data and have a model of the representations that led to that generation. And the second one looks like we need a theory of individual differences. We need some sort of psychometrics. And so to us, the wisdom of the crowd looks fundamentally like a cognitive modelling problem with these cognitive process and individual differences models needed. Mark said pretty much the same thing yesterday, so this is our approach. Use cognitive models of the processes that generate the data, and the individual differences across people as the bridge between the data that were observed and the latent knowledge that is what we would like to aggregate across. So we have this idea of different people potentially knowing different things, different parts of the puzzle that need to be put together, and all of that passes through individuals' cognitive processes to generate the individual behavioural data that we got. So we see our job in Wisdom of the Crowds is to develop a cognitive model of the processes that generated the data. That allows us to use inference. Bayesian inference we'll always use to make an inference about what the latent knowledge must have been that generated those processes, given the assumption that generated the behavioural data, given our assumption about the processes and the nature of the individual differences. And so all of the approaches I'm going to pursue, all of the examples I'm going to pursue are going to look like that. In all of the cases, I would say that sometimes our cognitive models are not very sophisticated cognitive models, and our models of individual differences are not very sophisticated ones, and we would like incrementally to do better. One of the nice things about Wisdom of the Crowds is you can always test whether your model is useful, and you can test it in 2 ways, whether it leads to a good answer, whether it leads to a good prediction or a good inference about the latent knowledge, and whether you can say something about the individual differences in the people, particularly their levels of expertise. So here's the first one, ranking expressions of knowledge. Mark also talked about this a bit yesterday. So way back in 2010, I think this is the first time we started doing this, we had 135 undergraduates in the building just across here predict how the NBA West would finish in its final order. And it was about 10 games into a 74-game season by the time we decided to ask this. So an individual might have given a list like this. Here are the 15 teams in the NBA West. And it turned out that season that it looked like blue. This was the answer. And so you can measure how well an individual did by the Kendall's tau measure that Mark talked about yesterday, which is the number of pairwise swaps you need to do to convert their green order into the true blue order. It's a measure of error or distance. Yeah. It says, yeah, sorry, NBA West. I'll do the East as well. There are 135 undergraduates in the building across here.
No, but I mean, it's like somebody who never watches basketball.
There are 135 undergraduates across here. It's everything I know.
They didn't care. I mean, you didn't care.
I don't know. So I imagine some of them were experts who watched it and some of them didn't. 135 undergraduates. So Kendall's tau is a measure of distance. And you can see this person would have to do only 5 swaps to convert their answer into the true answer, and then they would get the right one. So their Kendall's tau would be 5. 0, of course, would be perfect. The bigger tau gets, the worse they're doing. So how well did our undergraduates do in doing this? The best possible answer is shown here by green, so that would be the perfect order, a tau of 0. If they somehow managed to reverse the order completely, that would be the red dot. And if you did things by chance, if you just threw down the 15 teams in order, you would get the dotted line distribution of tau. So that's the chance distribution of tau. So now I'm going to measure the tau of those 135 people, and I'm correctly labeling it West now. And all those little stick figures show the distribution of the ability of people to do it. You can see some of them were very good at it, some of them were sort of worse than average chance, and there's a whole distribution in the middle. So large individual differences. So the idea of our cognitive modeling approach would be to develop a model of how people produce those rank orderings with their individual differences and use that to infer the true rank ordering or the latent rank ordering that's assumed to be driving their behavior. The model we turn to do that, the psychological model, is a very simple one going back to Thurstone in the 1920s, 1930s. It's still used in psychology today. Bockenholt and others have looked at it. It's in the statistics literature, Marsden and Lin, used as a way of aggregating ranking data. And this is exactly the model Mark talked about yesterday. So the assumption is that each team has we're only showing 4 of the teams here, but each team has a latent ground truth on some strength dimension denoted by the mu's. And every individual, when they come to produce their rank order, samples from a distribution for each team that's centered on that mu, but has a standard deviation sigma that's now associated with the individual. So every individual has a Gaussian centered on all of those mu's. They draw a mental sample, the little crosses, and the rank ordering that they produce as their behavioral data is the ordering of those mental samples. This means that if an individual like individual 1 there has a smaller standard deviation, they're likely to produce something very close to the ordering of the mu's in the latent ground truth. If an individual like individual 2 has a larger standard deviation, they're going to be less expert. There's more possible of transpositions in the mental samples that they draw. And so this example down the bottom here, this individual's done 1, 3, 2, 4 because they've sampled the blue before the green, for example. And so you can see this is a very simple model of the generation of behavior, but it has the key parameters that we want. The mu's correspond to the inferred latent strength that is common to all of the people doing the ranking. So in that sense, it's the group answer. It's the inferred group ordering. And the sigmas correspond to individual difference parameters that in a single scalar measure something like the expertise of an individual. So it's a very simple model of how representation and expertise generate the behavioral data, the ranking decisions we saw, and it allows inference about those. We did the inference in JAGs, so everything here is formulated as a graphical model, and this means we only have to write a few lines of code and press go, and we get an approximation to the joint posterior in a Bayesian way. And in particular, we're going to get an inference about the mu's and their order, and an inference about the sigmas, which will be about the expertise of the individuals. So the ordering of the inferred mu's gives the group ordering, and we can see how well that performs in terms of the Kendall's tau. So I've overlaid that in blue on top of the individual people that I showed you before. The blue circle is kind of the average response. The model, because it's probabilistic, actually produces a distribution of possible orderings, and that's shown by the blue histogram. We're comparing that here to the standard statistical method, the border count aggregation method that Mark talked about yesterday, that's shown by the yellow dot. So you can see that the model performs really well among the very best of the subjects and outperforms the statistical model. So that's...
Are the distributions of the data always symmetric?
Of the data?
The strength distributions around the mean, are they always symmetric?
Do you mean, are these always Gaussians? Yes. The second thing that we got was a measure of individual expertise. So the sigma is shown against the tau now. The sigma is the measure of expertise for each person, so the expected value that's inferred by that graphical model. Each person is a dot in this subplot. So we have the measure of sigma, and remember we got this after game 10 of the season, and then we have to wait until game 74 has been played to measure tau and see how well each individual did. But you can see there's a strong correlation or a strong genuine prediction here that has an 85% correlation of the relative expertise of the people. So going through this process where people never rated their expertise, we couldn't possibly have known the ground truth because it hasn't happened yet, but just looking at the pattern of agreement among people as inferred by the model gives a prediction of relative expertise that correlates very well with how it plays out once the season's done. The reason it said east instead of west was that we did both. Here are the examples for exactly the same thing with 148 people this time in the NBA East. Very similar set of results. I guess the wisdom of the Crowd-Thurstonian model doesn't perform quite as well, but it's still pretty good, and you still get the really good prediction about relative expertise. We also did it with the NFL that year, so now fewer people, 40 people, but they're ranking 32 items, and you can see that it outperforms every single individual in a strong wisdom of the crowd's prediction in this case, and you still get the correlation with expertise. For this last NFL one, we did it as part of a different experiment, and so we did some additional data collection where we asked people to rate both beforehand how expert are you at judging the NFL, and after they'd produced their ranking of the 32 teams, asked them how confident are you now that you've made that prediction. So a pre and post report self-reported confidence level or self-reported expertise level. And we can compare that with what the model was able to infer on the basis of just looking at their behavior. So we have that 0.86 correlation I showed you a moment ago. If you look at the pre-report and post-report, you would want the correlations to be negative. As people get more confident, you would want their error to go down, and that's indeed the case, but you can see the signal is much weaker. It's around about 0.3 as a correlation. And in a number of other non-sporting examples, we've observed this very consistently. And I think the key thing that is making the Thurstonian model outperform the border model is exactly this identification of the relative expertise of people. It's natural in that generative model that I showed you that experts will be upweighted. The opinion of an expert will be upweighted in generating the group prediction. And I think the way to think about it is like this. If you think about the NFL, for example, and you have these 32 teams, if a number of people have very similar rankings of those 32, there are 32 factorial possibilities. This hasn't happened by chance. There must be some signal that they're all drawing upon. So a cluster of people in this 32 factorial dimension space, the ranking space, indicates that that's where the signal is, and the people who are nearby that are the experts. So the wisdom of the crowd answer will be heavily focused on where the people have clustered, and it will identify the ones who are nearby as the high experts and the one far away as the low experts. And in effect, the model doesn't mechanistically do this, but you can think of it as upweighting the experts and downweighting the non-experts in forming its group answer, and that's why it's performing well. You can actually trace out that logic if you look at some of the examples. So if you look at the NBA East, I don't know how many people are basketball fans and remember back this far, but this was the year that New Jersey had won like 3 games or something, even 40 games into the season. They could kind of, even mathematically couldn't finish in the top 8 very early on, a historically bad year. And so they actually ended up finishing at the bottom, whereas Charlotte, usually a fairly weak team, was actually having a pretty good year that year. If you look at the border count, New Jersey comes above Charlotte, but if you look at the Thurstonian one, it's exactly the other way around. And so my guess is that people who knew about basketball, the experts, knew to put New Jersey at the bottom because they were doing very badly and Charlotte were having a good year. But people who didn't know anything about it would think New Jersey's a big market, they're a strong team, let's put them relatively high. Charlotte's a small market, let's put them lower. So the border count, by giving every person's vote an equal value, if you like, is outperformed by the Thurstonian model because of its ability to identify this relative expertise and upweight it in forming the group judgment. Not that we do any of those calculation processes, they just fall naturally out as consequences of the generative model for producing the behavioral data that allows for individual differences in expertise. Okay, all of that was just laboratory data though, and we're here to talk about crowdsourced data. So we have a long-standing collaboration with a company called Ranker, a social media crowdsourcing company up in Los Angeles. It runs a big crowdsourcing opinion site. About 20 million unique visitors a year give opinions on tens of thousands of lists. Some of the lists are not very interesting from a scientific standpoint. Some of the lists are, some of them could even be thought of as predictions, scariest threats to the United States or the worst NFL teams of 2015. The collaboration with Ranker is really nice. They give us back-end access to their database so that we can go and look at all the behavior that happens on the site and use it. So here's the ranker.com list we're going to focus on, and we have some Germans here, so they'll be happy about this. Who will win the 2014 World Cup? There are two types of behavior that are going on here. One is ranking behavior, where people can do a rank, and this can just be a partial list of the team. You don't have to go through all the teams in the World Cup, so it's just a top-in list, and then others can come along and re-rank it. So we have a whole lot of ranking data, as we had before, but now partial ranks. And the second thing that people can do is vote thumbs up or thumbs down. It's a little hard to see because the list is closed at this point, but people can come and press a yes or no button to whether they like that team or not. So now we have, and this is an interesting cognitive modeling problem, two sorts of behavioral data that both speak to the same latent ground truth of the strength of these soccer teams that we would like to be able to infer. So we have the same latent strength generating ranking data on the one hand and voting data on the other. So we generated a model that tries jointly to model those two behavioral sources in terms of the same latent generating strength. The ranking model looks very much like the one I just went through. It just allows for top N, it allows for the termination of the list at some point. The mental samples stop being drawn. The voting data says that the higher the latent location, the greater the probability of the upvotes, and just has a simple transfer or psychometric, psychophysical type function that maps latent strength into response probabilities for upvotes. So again, a very simple psychological model, almost a psychological measurement model, if you like. The second thing that well, let me show you that first. So the model now has the latent strength of the teams, the mu I, generating both the ranking data, the yi, exactly as before, but also the voting data, the v and the n, through that psychophysical function. The same latent thing is generating two behavioral sources of data. Yeah, Mark?
What is the meaning of the upvote? Like, I believe it should be higher?
It's never quite clear when you talk to ranker people. I think most people interpret it as I like that item, and without regard to position in the list. But it's not impossible that sometimes they're voting on whether they like it in that position in the list. There are no clear instructions on the site. Looking at some lists that we've been able to look at that kind of test this, where there's the best washing machines and the worst washing machines. So the things are reversed, which is kind of the logical manipulation you want to test what people are doing. It looks like they just care about the item, not about its position in the list. So we have those two behavioral sources, but we have one other really important source of information that I think is nice in this application, which is Sepp Blatter, remember him, drawing marbles from the jar to decide which teams go into which groups within the bracket structure of the tournament. And this is really important in predicting the outcome of this tournament, because by definition, of the 4 teams in any one of these groups, 2 are going to finish in the top 16 and 2 are going to finish in the bottom 16. This is an important prior constraint that you could bring to bear. And so that's something the model also does. The little calligraphic B that's donated over the muis means that that prior knowledge is implemented as a prior over the latent strengths of the team. So that structure is imposed within the Bayesian model. So we fed in the ranker data and we imposed Sepp Blatter's bracket constraints and ran it through and made predictions. Here's what it looked like. So we predicted Germany to win and to beat Brazil and then Spain, and running all the way down to Iran at the bottom. You can see the voting data on the left with the upvotes in grey and the downvotes in black. And so you can see both the number and the relative proportion of up and down votes for each of the teams. And you can see the ranking data. The bigger the circle, the more people rank that team in that position. So all of this information's been combined. You can also see the effect of the bracket prior information with teams like United States and Portugal, drawn in tougher groups, ranked a little lower than you might expect based upon the behavioural data, and a team like, say, Algeria or Nigeria, drawn in a relatively easier group, ranked a bit higher than you might expect. Or Switzerland, actually, speaking of Blatter. Okay, so how well did this prediction do? Showing you the same sort of graph I've shown you before. The best possible is shown over on the far left in terms of now partial tau, because we're dealing with partial orderings. You can see that when we included the rank and the vote and the bracket information highlighted by red, we made a really good prediction that outperformed anything that any of the individuals on the ranker site did. It also outperformed dropping any of those information sources. So rank and bracket shows what happens if you took away the voting data, and that does worse. Rank and vote shows what happens if you took away the bracket prior, and that does worse. If you just use the ranking data or the voting data or just the bracket data, all of those are shown, and they all do much worse. We also had a look at the border count. You can see that there. We had a look at 2 betting sites, Betfair and 538, and had a look at their predictions, and we're outperforming all of them. So I think this is a nice example of the way you can use multiple sources of behavioral crowdsourced information plus extant knowledge you have about the structure of a tournament to come together to make a prediction, and that you need all of those sources to make the prediction as good as it can be. Yeah?
Did you ask them to compare any teams or only the teams, only the possible players?
We didn't ask them anything because we're getting these data from a real-world crowdsourcing site. So we got the data that people had put in the crowdsourcing site, which is a bunch of ranks and re-ranks and a bunch of votes. We can't ask them anything.
Sorry, I might have missed. How many rankings did you get? Ballpark?
20. However many stick people there are.
Oh, okay. Sure.
Yeah. People tend to vote a lot more than they rank on this site. With a few exceptions. If you look at things like the top movies of all times, tens of thousands of ranks
So
there.
you beat all these. I mean, Betfair, I'm sure, had tons of data. You beat them to 27.
Yeah, because I'm on camera, Betfair and 538 asked a slightly different question, which will who will win, and we took the ordering of who they said was most likely to win. So if a Betfair representative was here, they would say we weren't optimizing against those criteria, and that's true. That's true. Bill.
How much worse do you do if you assume everyone has the same standard deviation?
That would be the border count, because you'd be giving every vote equal value, and so that much worse. Yep. Anything else? Okay. Tournaments is something I haven't got as far into as I would like, but I want to raise it as a possibility and give you one old example. So this basic Thurstonian approach we're using could be applied to predict any sort of sports tournament. And you can think now of there being teams, whatever those are. They might be genuine teams, but they might just be individuals participating in events. And those events might be tournaments or they might be games. For any of these cases, you've just got the notion that whatever participants there are, they have some latent strength, and an individual will rank with respect to them using their expertise, using exactly this Thurstonian model. So if you think about things like NASCAR and golf, you have all of these events, races or tournaments that have some subset of a large set of people participating in each of the individual events. You could apply this model to those sort of data. I have some data like this, but I haven't done the application. It would also apply to the most controversial thing going around in American sport, which is NCAA football, which I assume many of you are familiar with, where there are all of these teams playing, but very sparsely interconnected. They're mostly in their own conferences, and they rarely play across conference, so you have very limited data to do the ranking across the entire nation, but you need to do that to determine some Final Four, and currently that's done by a bunch of mandarins who kind of blow smoke up chimneys and guess and are open to bribes and who knows whatever else. So it's really just done by human expert opinion in a small room. You could apply a modelling approach like this to make some sort of inference about who the strongest teams in the nation are by just considering who would beat who in terms of latent strengths and applying all of the sparse data. I think this would be an interesting thing to do. The one that we have done is the March Madness college basketball tournament. We have some data from 2010. This is the biggest data set we have. It was scraped from the web. It has more than 16,000 people's March Madness brackets, so it's more than 1 million predictions about games when you take it all into account. Here are Obama's picks. It's a 64-team bracket structured tournament where teams play off in single elimination format. So we applied the model to the 16,000 that we had. We actually only did it in each of the 4 brackets. We didn't model the semi-final and the final. That's something I would like to get to. That's a nice big data question, but I'm not there yet. So now the worst possible thing you can do is predict 0 of the games. The best possible you could do is predict the 60 games that we're trying to model, not the semi-finals or the final. The chance distribution shown by the dotted line, the distribution of the 16,718 people we have data for is shown by the histogram. If you just followed the published seedings, you get the brown. If you followed the majority vote of what all the people who considered that game within the database would have picked, you get the yellow. Obama got the mauve color there, and our Thurstonian model does one better than Obama. I'm not sure this is a wonderful result. It's a decent result. What it does show is the applicability of this modelling approaches to very general sporting structure tournaments, and I think that's the takeaway message. Okay, now I want to talk about probability, estimate expressions and knowledge, and this is a little change of gear and some soccer questions. And because we're at that part of the talk, you know, we're 2/3 of the way through and we're starting not to listen anymore. Let me introduce you to Gordon Strachan. How many people know Gordon Strachan? One, okay. So he's my favourite Scottish-born English football player and manager. He has a great ability for answering soccer questions that reporters ask him by kind of unasking the question or pointing out the absurdity in all sporting interviews. So let's just spend a moment with Gordon. So, Gordon, what areas do you think Middlesbrough are better than you today? What areas? Mainly that big green one out there. What's your impression of Jermaine Pennant? I don't do impressions. So, Gordon, any changes then? Nah, still 5'6" ginger and a big nose. Gordon, can we have a quick word, please? Velocity. He keeps walking. I actually have 32 more of these, but we should move on. Okay. What we really did with soccer questions was ask people things a little drier. So this is now on MTurk, 145 people. I was doing the math yesterday. I don't think we paid them enough. I think this takes 15 or 20 minutes and we paid them $1. It's not way off, but it's $3 or $4 an hour. Okay, so if a team's leading in the 85th minute, what's the probability that it will win? We asked people what's the percentage, and we gave them a context, all European First Division games over the last 10 years, because that was the database that we scraped to estimate empirically the ground truth answers to these questions. Or what percentage of games that are 1-0 at full time, what percentage of all games are 1-0 at full time with the home team winning? And it turns out that's 11%. So people were asked 40 of these questions. We also had people self-rate their expertise with regard to soccer and answer 7 general knowledge questions, like who won the UEFA World Cup. Here's how well people did. So now we're measuring the mean absolute difference between the percentage answer they gave and the true ground truth percentage that we got by looking at a big corpus of games. So people are anywhere between 0.1 out and 0.4 out, and you can see for the very best person in green on the left and the worst person in red on the right, the scatter plot that shows their estimate versus the truth for all 40 of the questions. Okay, so big individual differences. So now we want to do exactly the same thing. We want to model the behavioral process that generated these data while allowing for individual differences, and then use Bayesian inference to make an inference about what the ground truth for these percentages were. So we have exactly the same idea of a latent ground truth. Now these pies correspond to the percentages that are the answers to the 40 questions that we asked. We have the same notion of expertise and people sampling their answer from a Gaussian, and the bigger the standard deviation of the Gaussian, the less expert the person is. But we have an additional insight from psychology now, which is there's a big literature on people being miscalibrated in probability assessments, overestimating very small probabilities, underestimating very large probabilities. So we built into the generative process that's trying to explain how they wrote 23 on the page, or whatever they wrote on the screen in MTurk, a notion of this calibration function. And here's the calibration function that we picked, shown by its distribution. So this is a prior predictive distribution for people familiar with Bayesian statistics. The thing that maps the true probability to the perceived probability, so the miscalibration. And you can see that it overestimates small and underestimates large, and it has a distribution of the strength by which it does that.
So it's just extremizing?
It's doing exactly that mapping, if you want to call that extremizing, sure. Yeah. And it's doing that mapping with the probability represented visually by the grayscale. Yeah. Or, if you like, this tells you everything you need to know to replicate it. So the strength of calibration is described for an individual by the delta, and that delta is given a prior, and that prior is the thing that corresponds to the grayscale prior predictive that I just showed. And otherwise, everything is working as before. We have ground truth probability that's being misperceived by an individual with their degree of miscalibration, and then being reported with their level of expertise, given by the lambda is now a sigma. Okay, so we ran this model through. It means you only need to see the behavioral data, the PIJs, the probability the ith person gave to the jth question, and you'll get an inference about the true crowd probability estimate, the pi, and you'll get an inference about the miscalibration and the expertise of each individual person. So if we do that, here are all of the individuals again. The red line shows how close or how accurate the model that had both calibration and expertise was built in. So that's our wisdom of the crowd's answer, and you can see it's among the very best of people and does a pretty good job in estimating these probabilities. If you take out some of the components, so if you just look at expertise or you just look at calibration, in this example you'd do worse. You needed both of them to do as well. And if you look at standard statistical measures like taking the mean or the median of the raw answers, you do worse again. So there's something to both the miscalibration and the expertise that helps you do better prediction, at least in this example. I think the miscalibration is important. I think the expertise is also important. Here's some evidence for that. Again, we have this really strong correlation between the inferred expertise of people and their performance once it's measured, and that correlates much better than either self-report or the general knowledge that we asked about, both of which go weakly in the right direction, but not nearly as strong as the model inference. And again, the model inference has the big advantage that all people needed to do was the task. They didn't get asked any additional questions. You certainly didn't need the ground truth. You just infer it from their pattern of agreement with other people. Yeah.
So the general knowledge, that looks pathetically poor. You think people just Googled the answers to your questions and plugged them in and didn't actually know anything?
They couldn't have Googled the answer to these questions. We had to scrape and then analyze 6,000 European games. We don't think these statistics are published anywhere on the web.
Well, the general
Oh, the general knowledge?
Yeah, like, you know, who won the 2008?
I guess they were just being honest and giving their best answer. Yeah, I mean, they get paid for just doing the task, and there's no financial advantage to taking longer to do it. Yeah. Sometimes when we've done general knowledge versions of these, so not sports, so I can't talk about it, we've tried at least to go as far as whatever the question is, if you put that question into Google, the answer doesn't appear on the first page of the hits, or something like at least enough control that it wasn't trivial to get the answer by doing some sort of search. We started applying this to other sporting contests, and now these are genuinely predictive contests. So 100 people to estimate the winning percentages of all 32 Major League Baseball teams for the 2013-14 season. And we started this actually partway through the season, but baseball goes so interminably long that didn't really matter. You can see in this case, calibration doesn't help, but individual differences does. I think if I'd been asked ahead of time, I would have predicted that. One of the things of having a 164 game season is everybody wins about half their games, and there's very little activity in the bit where you would expect the calibration curve to help out. But individual differences still helps, and you can see a really nice strong correlation between expertise and performance in this case. We never asked any trivia questions for this one. It was the first one we did, so we only had self-report, but it's much weaker. You can guess what's going to come next. Now we decided there are other sports, so we went to the NBA and asked 100 people to do the 2014 season. In this case, both calibration and individual differences help improve your prediction and outperform the mean and the median. And I think it's for very similar reasons. There's a really strong correlation between expertise and prediction, and it outperforms self-report and general knowledge. And then the one that's in progress, this is the knottiest one. I debated whether I should present this, but here it is. So we're currently doing the NFL season, and we're waiting for the season to finish. You can see the Patriots just dropped down last week. So at the moment, wisdom of crowds is working nicely. All of these aggregation methods are outperforming most of the people in the crowd, but we're not seeing the evidence for the calibration and the individual differences. Well, we're seeing none for the calibration and only a little bit for the individual differences. I want to see what happens when we get to the end here. This is easily the fewest number of games of any of these tournaments. They only go up to 16, and I want to get to all 16 to see how it works out. What we do have, though, is already the strong correlation between expertise and performance, better than the self-report and general knowledge. This seems to be incredibly robust. I'm already at my conclusions, isn't that nice? I think putting together crowdsourced opinions is useful for understanding what people think and making predictions. And I think both of those are important from a cognitive psychology perspective. The really useful thing here is just, did we make a good prediction? Just the statistical machine learning measure of, did we do a good thing? But there's this extra bit that comes about where, because you're thinking about individuals' expertise or you're thinking about their calibration, you get additional insight into why it is that a model might be outperforming. And I think that's valuable. I think the cognitive modeling approach here, we've really only just got started. I think not only does it give you the expertise and calibration and those other things that you wouldn't get from black box statistical or machine learning approaches, but it suggests other ways that you can tackle these prediction problems in the first place. I think the World Cup example was a nice example of that. The idea that the same latent knowledge can generate multiple sorts of behavioral data, all of which are jointly relevant for making the inference and prediction that you want to do, is something that comes naturally to a psychologist who recognizes that somebody's neuroticism generates this sort of behavior in this situation and this sort in this situation, that the same latent thing is generating multiple behavioral outputs. And that seems like a natural insight that comes from the cognitive modeling perspective that's very useful in an applied sense here. And then the final thing is, these have been very simple models. You know, these were Thurstone 1927 models with slight extensions. There are better models of cognitive processes like ranking and estimation and so on. And the better we get at modeling the behavioral processes and the structure of the individual differences that people had to generate their data, presumably the better we'll be able to make predictions and understand these things. Okay, I want to finish by thanking Mark, who's worked especially on the ranking stuff, but all of this with me, Brent and Mindy, who are no longer here but work on the expertise, and my current grad student Irina, who's worked a lot on the percentage estimation stuff. Thanks very much for your attention.
So,
Yeah.
I have a question. So bringing together your talk and the one by Sid yesterday, who found that there are certain things happening with the M-turkers, I was wondering whether you observed in your data that later predictions by the participants had less variance.
It's a really good question, and I started thinking about this as I listened to Sid talk yesterday. I think the answer is no, but only for the trivial reason. We only asked 100 people. That was the first bar of Sid's graph, and these were collected in 45 minutes. These were done so quickly that whatever communication happened, if it wasn't immediately within a family or two people who are already on a chat board, it didn't happen. But the data I saw yesterday from Sid would make the prediction that there would be a richly structured form of individual difference and similarity with respect to time and completion because of these social processes. And if you were really good, you could model that. I mean, that's what you should do. You should be modeling that so that you could factor out the bits that were communication and preserve the bits that were genuinely independent knowledge to preserve an average. That would be a rich social cognitive modeling approach compatible with this framework, but too hard to think about right now.
Maybe even then with undergraduates also.
Yes, I mean that was a more controlled experiment, so I'm more comfortable that they were independent. You know, they were sat separately in booths at the same time. They look more like your classic experimental
They were
laboratory
on the
data.
same campus, right? They would maybe communicate with each other.
Well, but even more strongly than that, they did better in the West than the East, and that's no surprise because the Lakers is much bigger here, and so people follow the Western Conference. And sure, this thing. Yeah, Bill.
You've been using comparison of the truth, showing that this model does a lot better than Porta and so forth and so on. Have you developed the posterior predictive checks for this Thurstonian model?
We haven't, in this work, we haven't looked very carefully at the posterior predictive because we're motivated by, we don't actually, the model's wrong, horribly wrong, and we don't really even care how wrong as long as it's useful. And useful here,
Correlate pairs of people and factor analyze it, you probably would predict a one factor.
I think this model's ability to regenerate the data in a posterior predictive is probably not all that impressive. And this is the one time where I don't care because this is genuinely a prediction. You know how often scientists talk about prediction, you know, that's in their figure caption, here's the prediction of the model. And it's not a prediction at all. It's the thing you got after you put the data in the model and let it tune its parameters to the best thing and put it back. These are genuinely predictions because we're asking people 3 months before the answers are known. So if it can perform well, I'm going to call it a good model, especially if it also measures things that are predictive of how well they're going to do, like their expertise or their miscalibration. But to the last point I made where there's scope to do even better if we generate better models, that's when you have to have a serious account of how well am I able to describe the behavioral data that I currently have, those traditional cognitive modeling metrics. And so they would be important for that purpose. Yeah, Mark.
So I don't know the literature on desirability biases that well, but suppose you're a fan of the Netherlands, would you sort of have a bias to more than it should. And so if you know the origin of a fan or their
Yeah.
allegiance, incorporate that into the model, I think you can titrate out
Absolutely. So a little bit like the grand social cognitive goal over here, that would be the grand psychometric goal. At the moment, our model of psychometrics is people have a single number associated with them, which is how expert they are, or that plus a calibration number. You could have a much richer model of a person, including covariates like how old they are, where they came from, and in some of the ones like the ranker data, we have access to those demographics, and it would be interesting to do. You would then want to build a model of how those demographics influence the generation of behavioral data, and picking your favorite team or putting the team you really hate down the bottom. Well, it's Dutch. I usually hear it in Belgium. That thing, soccer is a game that goes for 90 minutes and then Germany wins. So I imagine those people want to put Germany somewhere down the bottom on the basis of this understanding. So yes, a richer model of individual differences, both observed and inferred, and how that relates to the generation of behavioral data should do better and should give you greater insights. I agree.
Well, sometimes more complicated models do worse when you're estimating too many parameters given the amount of data you have. So that would.
But we're Bayesian.
Excuse me?
But we're Bayesian.
I was going to ask, your calibration model, I think, could be improved by having a parameter that moves the whole thing up and down. So
Yeah, it's possible.
the model you've got there at 0.5, people are always well calibrated.
Yeah, so that's right.
Some people that are optimistic or pessimistic,
That's
I
right.
don't know what word you want to use for it, but at a true probability of 0.5, they might be high or low.
Right, so the model we have is the linear and log odds with absolutely no intercept. There's a whole, as you know better than me, there's a whole family of class of models that could be explored here. The reason for picking that one was, it was the simplest one that got the effect that I was very confident was going to happen. And I wanted to not do the wrong thing and just put vague priors on things because I didn't know. I wanted to put an informed prior that I thought matched the way the data were going to look. So the prior has serious theoretical content. I could see how to do that. For the degree of miscalibration, I wasn't so confident that I understood whether things were going to be over and underestimated. But that just might be my lack of knowledge of the literature, and that could be done better. I'm agreeing with you.
Talking about a more complicated, talking about a little bit more complicated model, a parameter that moves that.
Yeah, I understand.
down.
I understand. It's what would the prior on that model be was not immediately obvious to me, so I shied away from it.
For each individual subject, you could have a prior to it, but we don't have one.
Yeah, you would have to then have a whole lot of demographic information about that subject and some theory about how they related to that parameter. Yeah.
These are probably kind of random shots. I was thinking of this in the context of the prior paper too. I couldn't find it in an internet search. Howard Weiner, when he was at ETS, had this example where there was a math error found in one of the questions. And it turned out to be an error that fooled the students with the best scores.
Right.
So it's probably an exception that proves your rule, but it was the people with the most expertise who were misled by the phrasing.
Yeah. If all of those people are sitting on the wrong answer, we're going to get this horribly wrong. And there's no doubt about that. We've tried to do this by doing things like asking our undergraduates what language is most commonly spoken in Brazil. And for once, we're hoping our undergraduates will give us the wrong answer. You give us the wrong answer the rest of the time. Could you please just do it again? But they actually get that one right. We don't have the data that we would ideally like to test this. I think if in isolation everybody believes the wrong thing, I don't think cognitive modeling is going to save you there.
And then the recent research by Barb Millers and Tedlock are finding expert predictors. They're experts across a lot of domains.
Right. So
You haven't looked across domains.
No, but it would be a natural and easy thing to do within this cognitive modeling approach. So the idea then would be that the psychometric model is richer and it has dimensions corresponding to, I don't know, this wouldn't probably be verbal expertise anymore, but this would be sporting expertise or just basketball specific expertise, some sort of factor structure model that people loaded upon, and by looking at their behavior across multiple repeats of the same sport and across different sports, you should be able to build up inferences about this model, and that should improve prediction a lot. Yeah.
Your measure of expertise being better than general knowledge and self-reporting.
Right. In short, you want a much better psychometric model, and then things should improve. That's right. Yeah, sure.
Just an idea, maybe along the lines of sophisticated models with more data. Have you thought about collecting data after every game? I mean, you could presumably do that. Say the same subjects in the NFL for 16 games, you could collect data every week, and then there's some idea of how the prior at the beginning of the season, how winning streaks or how much winning or losing affects certain.
Yeah, so I think that would give you a whole lot more data. It would be a little bit like a wisdom of the crowds within, which Mark talked about yesterday, rather than a wisdom of the crowds. I think one of the interesting modeling questions that would come up there would be sequential dependencies in people remembering their previous estimates. So the one time I have looked at this a little bit is in power rankings that people produce, where they rank, say, each of the NFL teams every week. One psychological signature I think you see in those data is people overreacting to a single game. So because one team had a bad loss, they go from 3 down to 9 or something like that. If you could build a model of that overreaction and factor it out in your inference about the truth, I suspect you might be able to combine people's sequentially related judgments in a powerful way to do better estimates. But those are just ideas. Look, I gave you 10 minutes of discussion before lunch. It's awesome.
So thank you again.
Yeah.
Thank you.